When most people think of hot, they imagine red. For example, red lava or red hot metal or even red warning signs. So why is it that in physics, blue fire is actually hotter? A candle burns orange, a gas stove burns blue. And the hottest stars in the universe, they aren't red, they are blue. Which means somewhere along the way, human intuition got temperature completely wrong. And the answer starts with something that we rarely think about. What fire actually is. Fire isn't a physical object, it's energy becoming visible. When fuel burns, atoms and molecules get violently excited. Particles collide constantly, electrons jump between energy states. And during that chaos, energy escapes as light. That glow you see in a flame is not random decoration. It's a temperature revealing itself. And once scientists realized that, they noticed something strange. Hotter flames consistently shifted towards blue, which raises an even deeper question. Why would color depend on temperature at all? Light doesn't travel as a solid beam. It moves in waves. Some light waves are long and stretched out. Others are short and tightly packed. Red light has longer wavelengths and lower frequency. Blue light has much shorter wavelengths and far higher frequency. And in physics, frequency is directly connected to energy. So as the frequency increases, energy increases too. That's why hotter objects begin shifting toward blue. As temperature rises, atoms vibrate more violently and release increasingly energetic light. The color transformation follows a pattern: red, orange, yellow, white, then blue. Blue fire is not powerful because it's blue. It appears blue because it contains high energy light. And long before modern physics explained any of this, humans had already noticed the pattern. Color became a way to estimate temperature simply by observing the glow of fire itself. Long before equations existed, humans were already reading temperature through color. Blacksmiths knew metal changes color as it heats: dark red, bright red, orange, and then almost white. They didn't know about photons or wavelengths, but they trusted the pattern because nature repeated it consistently. The hotter the object became, the brighter and bluer the glow started shifting. In a way, the universe had been visually exposing the loss of energy for centuries before the humans understood the math behind it. And this same rule doesn't stop with metal workshops of fire. It scales all the way up to the stars. Our sun looks yellow-white, but some stars are far hotter, and those stars glow blue. Blackbody radiation explains why this happens. As objects get hotter, the peak energy of the light they emit shifts towards shorter wavelengths. So it means towards blue. Some blue stars reach temperature above 30,000 degrees Celsius. That's several times hotter than the sun. And what's fascinating is that the color itself becomes a temperature map. Astronomers can estimate a star's surface temperature just by analyzing its light. Which means color is not just something we see, it carries a physical information about reality. What looks beautiful to us is actually physics communicating through color. Every flame, every glowing object, every star in the sky is constantly broadcasting information using light. Temperature becomes color, energy becomes visible, and your eyes quietly decode those signals without you even realizing it. Which means blue fire isn't just hotter than red fire, it's just a reminder that color can reveal physical information about the world around us. Something as ordinary as a flame is quietly showing us temperature, energy, and the behavior of matter, all through light.